Well, it's great to start the new semester theory seminar with a great speaker. So Stefano Leonardi is the, he's heading the research group on algorithm at the computer science department at the University of Rome. And it's more than the University of Rome, is Spienza University, which is Homo Special, it's the Wisdom University. So Stefano has a lot of honors and record. I just mentioned that he received the ERC, which is the highest, the most prestigious research award in the European Union, and he recently became ACM Fellow. So we're going to hear about the wisdom in Rome. Okay.
Thank you very much, Heli. Thank you for the invitation. I'm very glad to be here. So I'll talk today about learning markets with two applications, first price auctions and bilateral trade. So this is a joint work with this set of co-authors, Nicolò Cesabianchi, who is, probably one of the biggest experts in online learning. And of course, most of the credit go to my co-authors, especially to the younger one, so my former student Federico Fusco, and then Tommaso Cesari from Ottawa, and Roberto Colomboni, also from Milan. So the question we like to answer is a good mechanism that deal with limited information about agents. Actually, mechanisms that not only deal with limited information, but perhaps they have just no a priori information. So they need to understand how the market is done. They need to understand which are the preferences of the agents. And the way we usually do in order to acquire information from the markets is either through sampling. So, for example, sampling from prior distribution, which are often assumed, especially in economics, to describe the type of the agents. But in some cases, these distributions are hard to get, or maybe there are just no distribution at all. And the other possibility, and there's been still, anyway, a lot of work in this direction, a lot of recent work, and the other possibility is the one of learning as we do, learning in the strategic interaction with the agents. So that would be the focus of this talk. With two applications, with the two main applications, the first one is on repeated first price auction. And the main goal, and the second one would be on repeated bilateral trade. So when bilateral trade is the problem of intermediation between a buyer and seller. So the mechanism is in the middle, and we'll propose a price that will let the buyer and seller to agree on exchanging a good. While first price auction is the problem where the mechanism will actually bid for our application is mostly in the advertisement world, so we'll bid for some impression, and together with other agents. And the one with highest bid will win. Yes?
So for the second bullet, which entity is running the online learning?
The mechanism, which is the intermediation, the exchange, which is in the middle, in between the buyer and seller. So the agents will be the buyers and the sellers. So in both cases, what we really like to understand is which is the impact of the information that is available to the mechanism on the learning rate of the algorithms that we design. Right? In particular, on first price auction, we will evaluate the impact on the learning rate of the so-called transparency of the platform in terms of revealing the bids of the competing advertisers and the valuations of the advertising options. In the second case, we'll evaluate the impact on the learning rate of different types of mechanisms, as for example, either direct revelation mechanism or posted price mechanism, which is two broad classes of important mechanisms.
So sorry for interrupting you.
No, no.
We'll just let the audience get food real quick.
Absolutely. So let me stop.
Yeah.
And actually,
That's
a good time also to make questions. So whatever, all the questions that you like to make on the model will be great. And then I will go very, very slow in the beginning because just to let you to understand what we are talking about. so
in this case, do I have any assumption on what the buyer and seller is doing?
Here we'll have a different type of environments. Either we'll deal with either an adversarial environment with no assumption at all, or with a stochastic environment where the buyers and sellers or the bidders will follow some distribution, which is set in advance, but it is unknown. So you can think of an adversary that will decide in advance on the distribution.
But the focus is on how the learning rate in particular affects. Once you fix those assumptions.
Yeah, which will be the learning rate. Question? Yes. First is a one-sided market. So the agents are on one side. The mechanism is not an agent. The second is a two-sided market. So the mechanism is in the middle between buyers and sellers, and they are both strategic agents. So they are very different type of agents, of markets, while we know optimal results for one-sided markets like the VCG mechanism or the second price auction, we know that maximizes social welfare. For the second type of markets, so bilateral trade, two-sided markets, there are not such results. They don't exist. It's impossibility results. We cannot maximize social welfare with an incentive-compatible mechanism that will align the agents with the mechanism. And we reveal the truth, so we let the agents, the mechanism to play on behalf of the agents. So that's not possible. So there's many interesting questions in there. And that's not possible because there are money that goes from one side to the other. And so let me start with the first application, which is first price auction with unknown valuations. So here we are in a setting where there is complete lack of knowledge. So we know basically nothing. We don't know what are the other competing advertisers. So we don't know even the value of the advertising options. We'll see why this makes sense. First of all, first price auctions become even more relevant recently because the advertising market moved from second price to first price auction officially in 2019. So because a set of reasons that offer higher revenue, and indeed in the strategic interaction with the market, the first price auction exhibit good equilibria, better equilibria than the second price auction. Though second price auction is the canonical solution because it actually owns all the nice economic properties, incentive compatibility, maximize social welfare, but actually there are recent work that explains that whenever agents play together, we play with the first price auction, actually they actually converge to the price, converge actually to the second highest price. So does more or less what we really want that the market does.
So when you say better equilibrium, you mean it's sort of more
Stable,
stable?
stable equilibrium, even stable, right? Not
Stable over multiple.
over multiple iterations, right? There's a very nice recent work on Nissan that shows this experimentally.
Well, stable wouldn't be good. There has to be some other feature of the equilibrium as well, right? Stable could be, zero or something, right?
No, stable and actually converge to the price to the second highest price.
Okay, got it.
So that's actually what we like. But that's not what I'm talking about today, but there is a number of reasons, and recently also more and more theoretical explanations of why first price auction is not that bad. So that actually changed completely the advertisement industry, that moved to managing the advertising campaigns with software agents, the so-called auto bidding systems. So the auto bidding systems will actually act on behalf of the advertisers, and then they will place the bids in the advertising markets on different campaigns, and will try to optimize some utility function. So we actually, what we do is we study these repeated first price auctions from the perspective of a single bidder. So the mechanism that we discuss will be the software agent that manage the bidding on behalf of one single advertiser. And the rest of the world is actually modeled as the highest competing bid that comes from the other advertisers, and the evaluation of the advertising impressions. And in particular, we like to investigate then how important is this information, meaning how important that the platform, after every auction is executed, will reveal, for example, the highest competing bid, or how important that the agent, the software agent, knows the evaluation of the advertising option before to bid in a specific auction. So we like, and of course, this is maybe some information the platform doesn't want to reveal, but nowadays actually some platforms start revealing this information, which was the highest competing that should have, should have bid in order to win the auction, in case it is not. And the other piece of information which is relevant is the valuations that are not known a priori. Why? Because actually we don't know, for example, which is the quality of the prospective users, whether they will only after the auction is executed and the auction maybe is won, we will have feedback on whether the user will click on the ads or not click on the ads, something which is not known in advance. Well, so let me describe the model carefully. We have a sequence of time steps. So capital T is our time horizon. And now we assume that there is an adversary that will generate beforehand for every time step the values of VT and MT, where VT is the valuation of the advertising option, and MT is the highest competing bid. And these are all values that are scaled in between 0 and 1. Okay? So that's the rest of the world. That's the competitor. Of course, we'll have value MT, which is the best competitor. And this value is sealed in this envelope. We don't see it. And that's the value of the advertising option, VT. This is closed in a box. We don't see it. We don't know it when we bid. Okay? So now comes time that we need to post bid, that we denote by BT, and we need to decide on this bid without knowing VT and MT. So say, for example, that 0.75 is the value of, is a bid of the advertiser, right? And say that it's value. So is the competitor is 0.50, 0.5. So actually he wins the auction. After he wins the auction, the box gets opened. And in the box, we see that the value for of this advertising option for the advertiser is 1. Okay? So the utility of the advertiser is the value minus the payment. That's a standard utility maximizer model. Okay? Well, we know this only after the bidder receives a feedback, and the feedback is received only after the auction is concluded. So we know the value, and we may also know the highest competing bid, which can be actually very interesting information for the future. Is the model clear? Yes.
Don't we find out the value BT if we win the auction? Otherwise, we don't know that.
Yes, that's a one model. Yeah, exactly. Let's say that. We'll see all the different models that we can study. Other questions? Right.
Presumably, the value can differ. So by DT, you just mean the value to our particular bidder.
At time T.
At
For,
time T, right.
only for bidder, for our bidder. We have one single bidder. Right? We are taking care of one single.
Yeah.
So we don't care about the others.
Yeah, thanks for the clarification.
Right. Any other questions? Okay, so what our goal? The goal is to maximize the utility across the whole time horizon. So the sum of all time steps of the utility of the agent whenever at time step t, the bid is equal to bt. Okay? And we like to characterize the, say, the learning rate of our algorithm as customary in online learning by the so-called regret. What's a regret? The regret is the loss with respect to a benchmark. And the benchmark that we adopt here is the best fixed price inside. So it's just the best, the utility that is obtained by bidding, by posting the best bid consistently across the whole time horizon. So that will be the total utility obtained by the algorithm when the bid is fixed equal to B across the whole time horizon. And we compare it with the actual regret of the algorithm that will adapt the bid depending on the past history and of, for example, the internal randomization of the algorithm. So these values is between are all, both values are between 0 and 1, all scaled between 0 and 1 at each time step. So the total utility is at most order of t, and our definition of learnability is that the regret will be the loss is sublinear in t. That means that these converge to the value of the benchmark as t becomes large. So we achieve basically something very close to the benchmark for a large t if the regret is sublinear in t. And we like to characterize this learning, this regret rate. for different models. Okay, so now this is a classification of the different degree of platform transparency that we can consider. So the most transparent setting is the one in which the feedback which is received at the end of the auction is complete. So we know the highest competing bid and we know the valuation. Okay? Even if we lose. So here we always know. I guess in the real world we may like to drop this assumption immediately, meaning that we don't really know the valuation if we lose the auction. We only know the valuation if the auction is won. So the other models differ for the information that we get with the highest competing. So in the transparent model, the highest competing bid is always revealed, both in case we win the auction, so in that case we know the second highest bid, or in case we lose the auction. In that case will be revealed the highest bid. In practice, some platform will reveal the information only if the auction is lost. That's a counterfactual information, say, next time you know what you have to do, right? If you want to, you need to pay more. So that's the so-called semi-transparent setting. We call this semi-transparent, meaning that the highest competing bid is actually part of the feedback only if the auction is lost. And then there is the bandit setting, so the less transparent one. In the bandit setting, the highest competing bid is never observed. We only get to know whether we win or if we lose, and if we win, we also get to know the valuation. So then the environments, yes.
There's never a setting where you would get the fee associated with the
Other
yeah,
with the other agents, no.
yeah, right.
No.
Valuation is specific to the bidder.
Yeah, the valuation is specific to the bidder. Some advertising option may value a lot for one bidder, may value much less for another bidder, right? Depends.
Right, but if you do something about, so you don't win, and then you know something about the other BT, whatever, then you might know, maybe I'm out, but you might know something about their strategy, like how that highest other guy is.
So the strategy space is defined by the bids. So that's the real decision, the action that happens. Anyway, it's actually quite maybe not very realistic that you get to know some private information of other agents. Right? Yeah. I mean, we don't consider it also because it's not part of the game. So we are looking at the game from the point of view of one single agent, right? And this agent interacts with the rest of the world through the MT. The MT is the is the interface to the. Yeah. So of course, if I know, for example, that this option is just crap for all others, I will bid very low. I agree with you. But there's some information that actually will also be acquired by the other agents, the agents of the other advertisers by playing the game. So they realize that the advertising options are crap, so they will bid very low as well. So, and then we will observe MT, and then, But good questions, excellent questions. Of course, there could be many other models that we could study. Okay, so the environment, the generation of these VTMTs, as I said before, could either be from independent identical distribution, which is fixed in advance, but it's unknown. So the adversary, in some sense, decides on the distribution, and then the generation is done according to the distribution. Or we can consider the full adversarial model. In the full adversarial model, the oblivious adversary will decide in advance on the sequence of VT and T pairs that will be played for the whole time horizon. In some cases, the adversarial model is too strong. Actually, we'll see that we'll have very bad regret bounds for the full adversarial model. And in those cases, in the both application, we want to make it weaker. And we make it weaker by considering a smoothed version of the adversarial model. So this means basically that the empirical distribution is constrained to differ from a uniform distribution for almost a parameter C. So we want to avoid these point masses that the adversary can just decide random values across the whole domain. So that means basically that the measure of the probability is bounded to be to the sides of the interval divided by sigma. So sigma is 1/10, is almost 10 times away from the uniform distribution, where the uniform distribution will actually be exactly equal to the sides of the interval.
So, I mean, it's very general. I'm not sure it's enough, but there is this game in practice where you force someone else to exhaust its budget. So here you assume,
No budgets.
yeah, that people who continue the game.
Yeah.
focusing.
No, I mean, there's all kind of literature with budget adoptions. And
Because I can just give higher bid, so that you pay more,
Yeah.
finish your budget, and then I don't have a competition.
yeah, that's an open problem in the end. What happens if there are budgets?
Okay, but
And that's a very good questions because indeed, I mean, the other BD setting budgets are a bit losing losing role, meaning that you have this concept of the return on investment, which is how much you want to get of profit. I mean, of value, extra value with respect to what you spend. Basically, I spend 8, but I want to get at least 10 across the whole time horizon, which is actually, so that's a very interesting problem. And okay, so this has been studied before in few papers. This topic of transparency, but actually the most relevant previous paper is the one of Bergman and Horner, but they actually studied how the transparency on the bidding will affect the equilibria that are obtained in a first price auction games. We can be there. We are just taking a different direction. We actually like to characterize how the information which is revealed will actually affect the learnability of the strategy. And previous work have been done also with unknown valuations, but they don't present worst case regret bounds as in our cases. In our case, and also there have been actually previous work that studied the importance of knowing the highest competing bid, and that gave worst case regret bounds, but in the case in which the valuations are known beforehand. So I think this work is the first one that actually give a complete picture of this problem when both the highest competing bid is not known and the evaluation is unknown.
What?
And the evaluation is also unknown. The highest competing bid
Also
and
unknown.
it's all unknown at the time. So online learning, we usually the results that we know about the expert setting, that's the one where we have a kind of a full feedback setting, or in the bandit setting, the one in which we have only a limited feedback on the outcome of an action. Those have these main assumptions. The first assumption is the one in which the action space is finite, and the objective is regular as a function of the action that is taken by the algorithm. And if this is so, transparency in our case regulates the ability to reconstruct the counterfactual information. So in the full feedback setting, actually, by knowing, for example, the highest competing bid, we have the information of what would have been the utility if we had a different bid, right? That is very important information for planning a future strategy. So in general, in the so-called expected setting, we have access to the counterfactual information. We have this full feedback setting, and the learning rate that are obtained from, for example, the edge algorithm is the square root t log k, where t is the time horizon and k is the number of actions. In the bandits case, the learning rate is best learning rate that can be achieved under these assumptions that actually don't hold in our case is square root tk. So yes. What? I'll explain in a second. Okay, so in our case, both assumptions are actually not true, because we have an infinite possible set of actions, all possible bid values between 0 and 1, and also, more importantly, the utility function is not regular. So the utility function is not, for regular means Lipschitz and continuous. So if we move a bit a little, the function shouldn't move a lot. It should just be bounded by some delta parameter. The variation should be bounded by delta parameter. So let's consider, for example, a distribution between two values of MT and VT that looks like that. So in this case, the valuation is bigger than the highest competing bid. In the second case, the valuation is smaller than the highest competing bid. So what's the utility in the first case? As the bid increases, the utility is 0 up to the highest competing bid. And then suddenly, as a jump to VT minus MT, right? It's first price auction. So if the bid increases, we pay more, and then the utility goes, decreases with a linear slope. That's the first case. But in the second case, we have different behavior, because in the second case, the valuation is actually smaller than the highest competing bid. So when we don't know either of them, right? When the bid gets up to the MT, so it's 0, the utility up to MT. When becomes MT, actually, it's equal to MT minus to VT minus MT, right? Which is negative. And then decrease linearly. So if you combine the two on this distribution, we get this shape. And this shape is not Lipschitz and not continuous. So we had to do something kind of new in the bid values, in the movement of the bid. Yeah. No, in the bid. Okay, so for dealing with the fact that we have an infinite number of possible actions, we usually deploy this kind of epsilon grid. So we don't consider all the possible values. We consider values that differ by a factor by additive epsilon. So it means that we have only 1 over epsilon possible bit values, right? The problem is that we should ensure that by approximating the bit value up to epsilon, we don't get completely different results, right? So in order to do that, we cannot actually have a uniform grid. We need to have a non-uniform grid that I will explain how to construct in one of these our model. While this is the stochastic ID setting, while in the adversarial setting, we can't do that unless we don't impose this smoothness condition. And with this smoothness condition, we can actually guarantee that the expected utility is Lipschitz. And we can use a uniform grid, which is something I'm not also I'll mention a bit later. So those are the main technical obstacles. And the type of result that we obtain are the following. So we, first of all, in the adversarial setting, without smoothness, we have a linear regret lower bound. So there's no efficient learning of a good bid strategy. In the case of stochastic, in the stochastic setting, we basically show that the full feedback and the transparent feedback setting are basically equivalent. So not knowing the value of the advertising option when we lose doesn't really affect the learnability. And we get this optimal regret bounds. The semi-transparent so here we always know the highest competing bid. In the semi-transparent setting, we know the highest competing bid only if we lose, but we don't know if we win. So this is kind of close to the adversarial setting, but still we can prove some, non-sublinear regret rate in the semi-transparent setting, but also in the adversarial setting if we have a smoothness. So that's more or less a complete characterization of the trade-off between information that is made available and the learning rate. So the take-home message is that revealing at least the winning bid avoids some pathological behavior that are used to construct this very bad regret lower bound. So let me show you one algorithm. And this algorithm is for the ID environment in the semi-transparent setting. So, and this explains you why knowing the winning bid only when we lose. So knowing the highest competing bid only when we lose, it's a problem. And actually, if we know also when we win, this helps us a lot. The big problem is that for making exploration, we actually need to lose, right? So the only way to get information is that we need to lose. So it means that the whole exploration phase of the algorithm, the algorithm gets 0. That's what we do. We have T to the 2/3 rounds of exploration, where we collect samples from the highest competing bid. But we can only do it by posting dummy bits, such as 0 bits. So we collect all these values. And now what we do is to build this non-uniform grid by selecting square root T0 candidate bits according to their ordering. So the ordering that we observed in the exploration phase. in such a way that the empirical frequencies in each interval is the same. So we have 1 divided square root T0 probability mass in each interval. And these bit values are not equally spaced as it is usually done. That's the first one. Now we have this non-uniform grid. After that, we have this non-uniform grid. We use the point of this grid as the action in a standard bandit tunnel. So what we get? In the first phase, these T0 rounds, we lose everything. So that's all part of the regret. It's one, just we lose one for each of these times. Then in the second phase, we have the standard regret, bandit regret. But the standard bandit regret is T times number of actions. And here the number of actions are square root T0. So it's T minus T0 times square root T0. But then we also have the approximation of the grid. The probability mass in each grid interval is 1 over square root T0 that we also multiply times T minus T0. And then we have the standard concentration bound. So by setting T0 equal to 2/3, we actually shall I do something? No. Sorry?
Yeah.
The
this is the
HDMI,
cable.
pull it and pull
Huh?
it, put it in and out.
Okay. Oh, thank you.
Can I ask a question or two?
Sure, of course. Yeah.
What, I didn't understand that. I thought I understood, but now I'm not sure I understand. Select theta root T0 candidate bits, meaning you look at you look from those exploration rounds, you look at the numbers.
The numbers that I got a number of set of values, which is the highest competing bids.
Yeah.
And here is
So candidate bid just means the maximum competitive bid.
right.
Okay.
Yeah.
And then this is maybe a comment. If you, I just want to see, it seems like this would extend in the sense that, so if your adversary knew you were doing this strategy, right, they'd be able to capitalize on your bidding 0 for the first number of rounds.
But this is IID. This is a stochastic.
Yeah. No, I know this is not,
Yeah.
this is outside your model.
Right. No. But you see, in the adversarial setting, indeed, you are perfectly right. You cannot play this game unless you don't put some bound on what the adversary can do, which is this move.
Some sampling, if you alternate or do something not always 0, can you sometimes get around that, or maybe there's a lower bound in there.
I mean, there is a lower bound for general adversarial setting, but if the adversary is smooth, so that cannot do whatever he wants,
Right.
he must respect some to be reasonably close to the uniform distribution. So then this kind of work.
Now, also, can you do this? Suppose you don't know T in advance. Can you do this so that
Yeah, I mean, that doesn't.
it shouldn't matter? But you're choosing T0 based on.
Yeah,
T,
I mean,
but-
that's usually you can learn T doubling,
yeah, that's
standard
right.
doubling tree.
Yeah. Okay.
The standard doubling tree
Yeah.
works.
Yeah.
Anyway, just say that you see that. Yeah, so in this case, T0 here is 2 to the 1/3, so we get all the T to the 2/3 bounds. Just balance out all this stuff, which is the best that we can get in the non-semi-transparent setting, and also in the adversarial smoothness. So, of course, I took much more time than needed. Maybe just give you some ideas of the second application. There are no questions. The questions actually on the first part? More questions?
Excuse me, may I ask a question?
Oh, yeah, sure.
Just want to ask, like, so basically, you're saying you want to select the candidate bids according to their ordering, such that the frequency of bids lands strictly in between like this kind of consecutive value. Do you know, like, whether this kind of like sampling would be efficient?
Sorry, I didn't get the question. Can you?
Oh, just want to ask, like, in phase one, step two.
If the algo is?
Yes, basically, I wanted to ask like whether it is efficient to select these amount of candidate bits such that their frequency is
Yeah. I think it is efficient. Absolutely.
okay. Thank you.
That's the feedback that we received from the platform. Okay, let me tell you something about this second problem, which has actually also received recently quite a lot of attention in literature. And here the problem is the one of designing a mechanism which does the exchange between buyer and seller. Maybe I want to get to the model. Probably I'm not getting to the technical details because there's only 10 minutes left. So, but tell you that that's a completely different type of game, because in two-sided markets, bilateral trade is the simplest version of two-sided markets. We have just one buyer and one seller. So we can obtain all the standard requirements of a mechanism that is maximize efficiency, incentive compatibility, which is truthfulness, so the agents are incentivized to tell the truth, and also individual rationality, the agents that are not losing money in the only if we allow the platform to lose money. So if we charge the buyer less money that we handle to the seller, right? That's actually what we don't allow. So this is the constraint that makes two-sided markets strictly more difficult than one-sided markets. So the mechanism shouldn't subsidize the agents. And here we have two versions. The strong budget balance means that the money that we get from the buyer we just move straight away to the seller, or weak budget balance means that the exchange can make a profit. So we'll give to the seller less money than he gets to the buyer, right? Which happens. That's what all our sharing economy companies do. And it's a very famous impossibility result. Not fully efficient means social welfare maximizing mechanisms for bilateral trade exist that satisfies incentive compatibility, individual rationality, and budget balance. So that's a cornerstone result in economics. A lot of work in recent years on finding mechanisms which are reasonably good, maybe as close as possible to the ideal optimal social welfare, while obeying these requirements. And this is not possible even in the Bayesian setting, even if we have some prior information about the agents. So we have a distribution from the buyer and a distribution from the seller. So for example, recent work has been focused on what if we have only limited information from the buyer and the seller, only one sample from the buyer distribution, one sample from the seller distribution. So very nice things can happen there, and things are possible. But if we had zero information, there is no approximation that we can get. We have zero information. So I'm not talking about that. But then the obvious question is, well, with zero information, no approximation is possible. But what if actually cast this problem in a repeated game in which we get information on the way? So we acquire information while playing with the agents. Right? That's the focus on this work. Just several papers, and more papers come out very recently. So the model here is that at each time t, a new pair or seller or buyer arrives. So now our learning algorithm is in the middle, in between the two. Wants to learn what? Which price to offer, how to price the buyer, and how much money to give to the seller. That's what we want to learn. So they have both private evaluation, then the learner posts a price. PT is the price for the seller, and QT is the price for the buyer. Again, this is done without knowing ST and PT. We don't know. We need to come out with a pricing without knowing exactly which will be the values. When the trade happens only if the seller is offered a compensation which is higher than its valuation, and if the buyer is after price which is lower than its valuation. Those are the conditions. So basically, we need to invent a number which is in the middle between two other numbers that we don't know. It's a simple problem altogether. Nothing really complicated. And the utility is the so-called gain from trade. So our goal is to move welfare from the seller to the buyer. That assumes that the buyer values a good more than the seller. So that's our ideal. And this happens if the price offered to the seller is higher than the seller valuation. If the price offered to the buyer is the price charged that we charge the buyer is lower than the buyer valuation. And what we get is the difference between the two. So buyer value minus seller value is the so-called gain from trade. This is also exactly equal to the sum of these three factors. Those are important because this is the utility of the seller, right? This is the utility of the buyer, and this is the profit of the platform, which is zero if the price is the same. The money that we get from the buyer, we give it to the seller. So same story as before. Again, from there, regret, want to optimize the regret. Let me observe that now the benchmark is all possible pair of prices, fixed pair. But for the optimum, if our goal is only the one of moving welfare from seller to buyer, it's just enough to have one value, right? In the middle. So this shouldn't be a pair, but the benchmark can be just a single value that is in between seller and buyer value. While actually we will see, I don't know whether we have time, that strategies that can differ, they put different prices to buyer and seller are strictly more powerful than strategies that have only one price, because by using two different prices, we can sampling separately from the buyer distribution and from the seller distribution. Okay, so even here we have a repeated game. And let me tell you which is the type of information that we obtain, which is the feedback that we received after that every exchange is played. So say the platform posts a single price, or could be two prices, BT and QT. And then after, without knowing BT and ST, without knowing the buyer and the seller value, But then after that, we get a feedback. What does the feedback tell us? We have three different models. So the full feedback model that we also call the so-called direct revelation, because it's similar to direct revelation mechanism where the agents trust the mechanism, will just reveal their values to the mechanism, and the mechanism will play on behalf of the agents. So at the end of the exchange, the mechanism get to know the exact seller and buyer value, which is not necessarily true in real life. Actually, in real life, they may just get 2 bits of feedback. So the feedbacks are the information whether the buyer agree on the price and whether the seller agree on the price, because this is enough to make the deal. They don't need to say, okay, I would have paid even more, right? That's usually doesn't happen. And one bit feedback is really the minimal one, where the exchange only get to know whether both of them accept. But maybe they doesn't know in case they reject. Of course, if they accept, both accepted. But if they reject, it doesn't know whether one or the other rejected. Right? Who rejected? Maybe one accepted and the other rejected, or the other way around. So that's the minimal amount of feedback that we can get, which is definitely less informative of the others. Indeed, we can't do much with this last model, but we can do things in these other two models. And as before, we study adversarial setting, and we study the stochastic setting, and also there are recent results, and also the smoothed adversarial setting. Because the adversarial setting is hopeless, because we can play this needle in a high stack game. So it's a very simple lower bound. So say that we have a randomized algorithm, and then the adversary just submits a deterministic sequence. That's using Yau's lemma. And then we can be the sequence where the probability that the randomized algorithm actually is able to put a price in the middle. Yes?
Sorry, I just want to remind you, you need to wrap. Yeah.
Okay. So that's almost 1/2. On the other end, the adversary generates a sequence that have a sequence where all the intervals have at least a common point. Okay, so there's always a common point that's the optimal price that he plays. But also these intervals are big enough, so they are almost 1/2. So you play with this, Cantor ternary set typical game. They move either right or left, and then you will see that the optimum actually has a utility gain from trade, which is T/2, while we actually can guess it only with probability half. We get T/4. So nothing is possible with regret. Adversarial setting, while in a stochastic ID setting, actually the adversary can play this game, and what is possible is try in a full feedback setting, basically acquire information about the past, and acquiring information about the past, playing just follow the best price. So follow the best price so far, given the information that I acquired in the past, right? Because in the full feedback setting, I get to know the BT and ST at each time step. And here we can basically, in the end, observe that the empirical distribution is converging to the true distribution, and therefore, these follow the best price will also approximate the benchmark in the long run. and we lose this standard square root t bounds. Just give you a bit of other results that we obtained. So there's a full feedback. So 1 bit feedback, we can do anything. So we have a linear lower bound. While for 2 bits, we still can play this ether needle and eye stack model. If the distributions are unbounded. So they are not, the distributions are unbounded, means they are not smoothed. But also we cannot sample the buyer and seller distribution if the two distributions are dependent. So what we require is independence and boundedness from the distribution. And in that case, we can obtain a t to the two-third bound. So here basically using leveraging independency, that's the expression of the gain from trade. We can separate the seller distribution from the buyer distribution. Once we separate this seller distribution from buyer distribution, we deploy an epsilon grid, and then by placing prices on this epsilon grid, we sample the two distribution, which is pretty standard now because we get this standard exploration bound. We get the approximation from the epsilon grid. So in t times step, so we lose epsilon t. This is 1 over epsilon squared, is just the exploration bound. And then we have the standard bandit regret. Again, as before, we have a bandit algorithm that plays just the prices on the grid that are 1 over epsilon. This is a number of epsilon. And here we optimize with t to the minus 1/3, and we get the t to the 2/3 bound, which is positive. So let me just conclude that has been, so we had this result also that says that if we have smoothened distribution, we get actually and we are allowed to post two prices, so we are in a weak budget balance, we get these tight t to the 3/4 regret bounds. While there are two other papers that studied the adversarial setting, one in the, say, weak regret model, so that's an approximation result. But this is not an approximation result. So even in the full adversarial setting, it's possible to obtain sublinear regret, but the budget balance is on the whole time horizon. Means that sometimes you lose, sometimes you gain, but over the whole time horizon, you don't lose. Okay? And then you can also beat the adversarial model. Okay, sorry for taking some more time. And there are, I think, a lot of interesting questions. For a bilateral trade, that's only single buyer, single seller. Don't know anything about multiple buyers and sellers. We don't know anything if the buyer, if the agent stay in the game across multiple time rounds. We don't know anything about revenue, for example, in this first case. For first price auction, in bilateral trade, we don't know anything about revenue or the platform. Soon that we want to optimize the revenue of the platform, the difference, how much they gain. And also for first price auction, there is a lot of possible natural extensions of these results. Thank you very much. Sorry for taking a bit.